Morning everyone, welcome to One Concept, Multiple Learnings, Multiple Tools. And today's concept that we will be discussing is more on related to conservation of momentum. Yesterday, if you remember, we had looked at what is momentum and how do you calculate momentum and how do you calculate momentum to kinetic energy and all this using these simulation tools. And today, we are going to have an overview of how do you apply the law of conservation of momentum, and then how do you apply this to the elastic collisions, inelastic collisions. How does it depend upon, or how does the conservation of momentum apply even in case of the what you call the center of mass? What happens to the center of mass in case of the elastic and inelastic collisions? That's what we are going to look into. Okay, so now let me share my screen. Just give me a moment. Go to the first one. Okay, so to begin with, I'm going to start with the first one, which is about a video. Okay, and then probably we might go for the rest of the simulation tools. This is from Texas Gateway, so one of the online resources. Okay, it's a really a good resource for one to understand, okay, based on the videos. The first video shown over here is something like this. There are two people sitting over here on two planks that have been connected to two wheels over here, and then there's a rope which has been between them, and they pull it across. And as a result of it, okay, we can see what happens to the momentum. Whether they move apart or whether they move nearby, and that's what we are going to look into. Let me just maximize the screen to have a clear effect on this. Let me run this. So this is what you have. See, both of them are pulling their carts towards each other. One was stationary, other one was seen to be pulling. So as a result of it, both of them moved nearby to each other. Okay, this is one observation. Let us move to the next one. Okay, the person in the cart is now having a huge ball with him, and he is going to throw it outside, sitting on the cart. Both of them are a system. And when he throws away, you see he's moving backwards, right? So even here, there's a conservation of momentum being observed. You can explain this based on Newton's third law of motion or maybe on conservation of momentum, because both complement each other. Okay, you can say using conservation of momentum, you use it, you get this, or maybe in the vice versa also. Now in this, okay, while I was narrating this one, for example, someone throws a ball to him, and as a result of it, he is moving backwards. So here also what happens is there is a momentum which is given to him, and he starts moving backwards. So I have represented these with the equations over here. You can look into the equations to understand what's happening over here. You can use this in your classroom sessions to show, okay, how the conservation of momentum equations can be applied in both the cases. I have a third one. Let's check it out. Then the second one is from here, which is actually a simulation where you can run this over here. So there are two objects given over here. This is a bit slow. I do not know. Maybe the way how it has been written is like this. I think it's a GeoGebra or maybe a Java one which has been embedded into this. And then what you can do is you can make it full screen. But in my system, if I make it full screen, it's running so slow. So I just tested this just now. So therefore, I'm not running full screen. I'm just using it like this. And shown here are two objects, object A and object B, whose velocities, direction of velocities are shown over here, which means this object is moving like this object is moving like this. Currently, the animation is freeze, right? And then you see the momentums of these objects are being given over here. Py is 0, that means the object is not going upwards, it's a one-dimensional motion. Px is equal to 6 units for object A, okay, which is nothing but mass multiplied by velocity. The mass of A is nothing but 2. Since it is 6 over here, you can say the velocity of A is 3 units over here. And the mass of B is also 2, so therefore equal objects are, and thus here you see VB should be equal to minus 2, right? This should be minus 2 and this should be plus 3. VA is equal to plus 3, VB equal to minus 2. And as a result of it, when I run this, and it says it's an elastic collision. And then when I run this, or maybe you can ask the student what kind of collision is this. Okay, and let me stop here. Let me stop this. Okay, now you see the object A has a momentum of -4 and the object B has a momentum of +6. You can ask them initially to write down the values of A and B before collision and after collision. And as you observe the momentum, the momentums has been exchanged. Earlier, this had a -4, this had a +6. Now this has become -4, this has become -6. So thus we can very clearly say the momentum has got exchanged. Okay. So this is a worksheet which has been taken from the same example, which was somewhere a link was available online. And then making use of this worksheet and the simulation, you can ask the students to work out the questions from here and get the answers for us. Okay, in fact, here this also accounts for the two-dimensional collision. As you see, this is VAF is equal to 0.48 I plus 1.1 J. J refers to y-axis. So that is also being given. So therefore, you can, when you are teaching the two-dimensional collisions, you can actually use this also. Okay, let me move on to PhD. So this is a smooth one. Okay, so it doesn't have any hassles like the one which we had seen earlier. So what you can do here is that you can actually see, for example, the masses of these can be defined over here, and then this can be played over here, this can be run over here. Let me just reset this initially, because already this was run. Let me reset this. The velocity of this particle is like this, velocity of this particle is like this, and it's completely elastic in nature. And then what you can do is you can run this across. When you run this across here, then what happens? They collide, and you see the directions are being shown this way. And there are a blue and a green arrow which has been shown over here, which tells you one is a velocity arrow. Green arrow demonstrates a velocity, which is a green arrow, and a momentum is indicated with the blue arrow. Right? The momentum and velocity are directed in the same directions because of just multiplied by a scalar value. Okay. And then you can also change the masses. For example, let me make, for example, one of the masses to be something like around 2.5 or 2.63, and this mass to be much smaller. Let me reset this first. It's not resetting. Okay, once let me reset this. The values, I cannot change the values of mass. Let me click on more data. It's here. Masses I have taken. I have reset this. Position is also shown. Velocity is -1.25 and 0.125. Let me make this also to be plus over here. Plus 2.0. Enter. And this is 0.25. So one is having a larger velocity, the other one is having a smaller velocity. They will definitely collide. That's what we need to do. When they collide, and if it is elastic, then what happens to the momentum? Momentum initially is 5.26 and 0.1. When they collide over here, then it's 4.03 and 1.33. So when you add these two, this again becomes a 5.36 over here, and earlier was also 5.36. Finally, see that the momentum is actually conserved over, right? Okay, let us move on to the next one. Okay, this is quite easier, but if you can click on the momentum diagram also, this shows you how the momentum was before and after, which is being shown over here. You can also look at the change in momentum, what happens to change in momentum. Okay. Reset this. Okay, you can get a change in momentum, you can center of mass, you can get the value of the center of mass, which is given by x over here. Okay, so initially when we start with this, we need not go for all these options, we can directly go only for the momentum conservation rule, because we are just teaching only conservation of momentum. We can go with this. Next is the worksheet, which you get along with this one here. Okay, so you can use PHET to actually run this worksheet, and the questions are being given over here. We can ask the student to take up the readings and then answer these questions based on the simulation given there. Next, there's one more example on conservation of momentum from physics classroom. So as you see, there are 9 diagrams being given over here. We can ask them to do as a classroom exercise. Okay, let me choose one of them. Let me take, for example, this one here. It says that the mass of the smaller fish is 20 grams and the bigger fish is going to be 80 grams. Okay, let me take up this value. I click on this animation over here. Smaller fish comes, it hits the bigger fish, and as a result of it, bigger fish has to move backwards over here. So now what we understand from here is that before lunch, the bigger fish has a momentum 0, little fish has a momentum equal to 1600. The total momentum was going to be 1600 here. After lunch, the bigger fish has a momentum is equal to 1280. Smaller fish had a momentum equal to 320. So some of these two will be again gives us to 1600. We need to work out on this. Okay, so that means usually what we consider is that when the fish gets inside the bigger fish, smaller fish gets into the bigger fish, we assume that the smaller fish is in contact with them and they are not moving. Okay, it's not being, it's already been swallowed, it's just there. But okay, which is not true according to this. It says that okay, as it goes away inside it over here, it somehow struggles and try to go inside. It pushes the fish along with it. And that's what this simulation tells you. Okay, let me go on. So all these are some different examples of conservation of momentum. You can use either of the tools, okay, depending upon what is that we are teaching across. Right. So this example, we make it a little bit bigger to make it clear to see it. So if at all for higher grades, let us say for example, if I have taught them about the conservation of mass also, the center of mass. If I taught them the center of mass also, nothing wrong. It's not there in your syllabus in IB, but maybe for AS and A level, if we have this, then definitely one can go ahead with this. Okay, but it also helps the student to understand more, okay, regarding this. Suppose if someone is doing an IA on conservation of momentum, then I think the discussion on this would be very much useful. So we can show this one here because it's just one small thing that we are going to show. And then what happens is, now let us say both the objects are being attached over here. And then after some time, when it comes to this point, you see that there's an explosion being seen. As a result of this explosion, both the objects move apart. Okay, let us see. Let us run this and show what exactly happens over here. Now the animation is here. The masses of these two objects are shown. Initial kinetic energy is 50 joules for the blue one. For the red one, it is 250 joules. Okay, and then the initial momentum of the red is 10, and initial blue is into 50. So total momentum, both of them are initially moving. Okay, total momentum of blue and red is seen to be 60 over here before the explosion. Okay, and then total energy before explosion is seen to be 50 plus 250, which is 300. Let us write down somewhere over here, right? But the velocity of these two bursts are seen to be 10 and 10, which means what? Both of them are attached together and they're moving together. Now let us run this. After explosion, these values will change and let's see what happens. Now when I click on this, goes until here and it breaks up and you see one of them has been thrown back, the other one is going here and this moves slower. See, let me pause it for a while to understand what's happening. The center of mass, okay, let me reset this once. The center of mass is on the black spot over here, which is in between these two objects. It's not exactly at the center of the blue box because you have a red box also here, so they are almost attached to each other, right? When I run this over here, until explosion, both the boxes are attached. Center of mass is also associated with them. Let me run this. Yes. Now when there is an explosion, now what happens to the center of mass? This is your center of mass. Center of mass is still moving, but it is not still attached to this one. Okay, so it is a little bit farther away, okay, from the blue box. Now let us read the kinetic energies. Kinetic energy once again after explosion. This is 50 and 10 before. Then this is 0.38 and this is 349.62. When I add these two, this becomes 350 over here. So here also this was 250 plus 50, which is 300 over here. Here it is in 350 over, right? Okay, let us understand why does this change over here. So if you look at this here, 250 plus 50, not be 350, be only 300. Otherwise, some extra energy has been given. There's something wrong over here. There is some amount of energy which is converted to other forms in the collision. Oh, that is why you are getting this one. Some push has been given over here, or maybe something has triggered. Some energy has been given to it, so that the collision has happened. Okay. Now, otherwise, this should not happen. Then, see here, you see the final momentum is 59.129. The final momentum for this one is 0.871. Comes out to be around 60 here and 50 plus 10, 60 here. So whether it's an elastic collision or an inelastic collision, okay, you observe that the momentum is seen to be conserved. This first thing that every student should know about it. Okay, and then you see the conservation of momentum, though these two objects are moving at different velocities. If I run this once again, if I run this here, This is moving at a different velocity, this is moving at a different velocity, but this is always moving at the same velocity. That means the center of mass of velocity before the collision or before the explosion and after the explosion has never changed. That's what we can understand from here. Okay, we can put it across all this. Okay, now let us look at this simulation here. So as you see here, you have two objects over here. You have an elastic and inelastic collision here. So now, if I make this to be 0, that means it will be a perfectly inelastic collision. If I make this to be equal to 1, then this becomes a perfectly elastic collision. Now, what do you mean by elastic and inelastic? Elastic is nothing but something where the energy is conserved along with the momentum, and inelastic is somewhere the elastic is not conserved, okay, after collision. Okay, now here you see the blue one has an initial kinetic energy of 250. The initial have of this one is of 96. What I will do is make this as 96 plus 250 around 350, which is 346 joules over here. Let me have a collision over here and see what is the energy here. We already know momentum is conserved. So like this. Now let us see here. So what's happening? This is 96 over here. This is now 50. And after collision, there is a kinetic energy 30.625, 315.37. So what's happening over here? When I add these two, 375 plus 625 would be 360, 316 plus 30 would be 346 once again. Here also it was 346, right? So therefore the energy is conserved. So this is a perfectly elastic collision. Now as you know, momentum is conserved, energy is conserved. That's what we can show. Now if I make this one lesser than 1, let us say for example, I make it 0.8, okay, and then let me reset this and run this. You can observe that the energies will not be conserved. See, the energy once again here it was 346 here, and here you see 225.094, and this is around 0.556. When I add these two, it becomes 225 plus 225.6. 225 plus 11 would be 236.6 something, right? 236.6. Some amount of energy is being lost because here it was 346 and here it's only 236 volt, right? So you see, kinetic energy converted to other forms of collision could be 109.3. It's not given, so therefore some amount of energy is lost. Energy is not conserved. That's what we can make it know. If I make this completely 0, I can tell them that reset this and make it 0. Then both the objects attach together and they start moving in the same direction. Okay, so this is what we can do, and we can show them the state transition diagrams also here. What happens? Okay, what are the energy diagrams? Okay, don't ask them to get confused with the energy diagrams that they learn in atomic physics. It's totally different. Okay, let me move on to the next. So once again, this is about the elastic and inelastic. And the difference here is that instead of using the animation, so this just gives you an idea about if I have the photo gates in your lab, then you can conduct the same experiment using the photo gates also. Let me just reset this. See, okay, one cart is here, the other cart is here. Maybe it is a table over here, and you can actually use something like a table wherein air is being made to pump through it, and as a result of it, the cart is made to move across here. Let me start the carts. Now you see, what do we observe here? The first one, 0.28, gives you the velocity of the pink color cart. 1.60 gives you the velocity of this one here, and 1.54 is the collection of these two. But if I add these two, do I get this? No, I should not actually add these two. But what I should do this one is, I should take the mass of this cart, weigh this one here. I get 193.1. This multiplied by 0.28, I'll get something. That is your momentum of the first one. And in a similar way, I'll put this down, I'll take this one, measure this one, which will be 439, multiplied by 1.6, I'll get some momentum of the second cart. And then I'll add these two together. Maybe I can add these two together. No, I cannot add here. But I already taken the masses of these two, add the two masses, and finally multiplied by this one. Okay, you will get some value. So that will give you the momentum. So the momentum that you get here and the momentum, some of the momentum that you get over here should be equal. Okay, so you can ask them to verify that because we have chosen this as an inelastic collision. The second thing that we can do is that we can ask them, okay, so find out what is the amount of energy lost because of these two getting attached over. You can do this. You can also change the same direction. You can change the opposite directions over here. Okay, or maybe you can say something like inelastic, partially elastic. You can do all these things, finally get the values over here, right? So this is something which you can do, really wonderful. Only one animation, okay, one simulation, you would be able to ask the students to calculate many things. Okay, the advantage of this simulation is that nothing else is given to you, and they need to work on this and then to calculate it. So it gives you something like a paperwork also in addition to watching the simulation. That's how it is being useful. We move on to the next one. Now this one, it's about bouncing with momentum. So what it tells you is that take up a football, take up a small ping pong ball, both of them attach it together and then drop it together. This could be an IA, and the moment it hits the floor, okay, it bounces back. And then we may ask, what is the height of the second ball? You can do a tracker analysis. In yesterday's video, I showed about how to analyze a video for one of the examples using the tracker software. You can do the same thing over here also. You can fix something like calibration scale. You can find out what exactly happens. You can do all these things over here. And so it's already given, okay, what is a experiment that one can do. So this is what we have given. You can use this one also. It's the same thing that you can use over here. Now, let me go on to the next one. Ballistic pendulum. I have not tried this, but maybe this year I'm planning to try this one here. Really wonderful experiment. You can have a wooden block. You can have two strings attached to it. Initially, let me reset this. Okay, it's being perpendicular like this over here. The height of this is given to be 1.06 meter, exactly the center of mass, and it's also in line with the ballistic, whether something like a bullet or maybe a particle which can get embedded into it. And then if you come down here, this is the mass of the wooden block is shown over here. I can vary this. The initial velocity of the bullet also I can change. Mass of the bullet I can change. What I can do is I can fire this one. Okay, I can fire this one here. The moment I fire this one here, it gets stuck into it. Okay, and as a result of it, you're giving some velocity and now it starts going upward like this, right? Let me fire this. See, it moves upwards over here and it starts oscillating over here. The moment it starts oscillating, we always think about having the time period, but here time period is not required. So 1.06 was considered to be the what you call the origin. Now, as it moves upwards, I can move the slider upwards over here, so it exactly matches the center of mass of it. See, at the center of this, yes, it's matching over here, 1.2 meters. Which means now I can say the difference between these two is nothing but the height that the block has been raised. And based on this, I can calculate what is its potential energy. Okay, I already have the mass of the bullet and velocity over here. So half mv square I can calculate. Half mv square was the initial kinetic energy, and then I can say that as it gets stuck into it, okay, it has been raised upwards. So therefore, the potential energy of the mass and as well as this one is equal to half plus small m plus capital M, mass of the block, into v squared. Okay, v square becomes 0, but m into capital M into gh, okay, will give you the total potential of the block, and the energy lost over here I can calculate. Okay, it will not be equal to this, so there will be some amount of energy lost. Why does it get lost? Because it gets embedded. Okay, it has overcome the force, okay, in order to cross or hit or penetrate that wooden block. Yes, you can find out that also. Okay, and then what you can do is you can actually change the mass of the bullet, or maybe you can change the velocity of the bullet. Usually we change the velocity of the bullet. If I increase the velocity, for example, let me reset this. I increase it, the same masses over here, I increase it to a maximum value here. Okay, and let me fire this. What is it you expect? You expect that this should go to a much larger height, right? So earlier it was 1.06. Let me pull this back to 1.06. Or maybe let me reset it like this. Now it's at 1.15. What is it? 1.55. Okay, my god. Okay, so this value is changed. Okay, that's the reason it's 1.15. Okay, so we're over here. Let me fire. Now it goes to a much larger height. Look at the center. Center is exactly 1.08, 1.03. Now it goes to much more higher. Take the maximum extreme point. This point. Yes, at that point, right? 1.42. And you can find out what is the height behind it and find out what is the potential energy. Thus you will be able to do it. Okay. So you can ask the question like, how does the increase in velocity of the bullet changes the height traveled by or height lifted by the wooden block? It could be a wood argue to work with this. Okay, but how long will this work is a question, because there's a friction associated with this. Ideally this works, but in a real case scenario, this may or may not work. Maybe because after two or three simulations, 2 or 3 times this one oscillations, it might come down to 0. That can also happen, or between every oscillation it might come down to 0. That's also possible. We do not know what can happen. And they should the object here should also be so cohesive that you should be able to take the object and then stick it over here, and then it should be able to move across like this, right? So you can do something like this also. The next simulation that we have here is the effect of dropping a mass on an oscillating mass. Okay, now we have something like this. You have a spring. Let me reset this. We have a spring over here. This 1 kg mass, and the spring is now made to oscillate. Now, as it oscillates, okay, a 2 kg block is dropped onto it. Okay, and as a result of it, what happens? Resets, right? So reset. Original amplitude is 10 centimeter. Original maximum velocity is 10 centimeter per second. This is on the spring. Original period is 6.28 seconds. Then total mechanical energy is equal to so much. Spring constant equal to so much. Okay, and either I can drop the object either here or I can drop the object here. When I click on this, object will be dropped. When I click on this, object will be dropped. Okay, let me try with this. When I click on this here, and then I click on this start button over here, it's not initially dropped to show you one oscillation. Goes here, comes back. Now it gets stopped. Now, as it drops over here, the original amplitude was 10 centimeter. This amplitude is also 10 centimeter. The original maximum velocity is 10 centimeter per second before dropping the object. Now the maximum velocity is 5.7735. It means the velocity is slowed down. The time period was 6.28. Since the maximum velocity is lesser, it takes a longer time to go to the one end and come back. So therefore, the period has increased. That means the time taken by the object to start from one end, goes to the other end, again come back to it, one time period has increased. Total mechanical energy is seen to be conserved. Spring constant is same. Okay, then if you want, you can now try the same thing with the center. Let me reset this. Now we have it at the center and restart this once again with the same values, and then find out what exactly happens. Now it falls here. Now you see amplitude has reduced. Okay, now the question is, why should the amplitude reduce? The maximum velocity is also reduced. That is understandable because you have a much larger value. And then original period has increased. It takes a longer time to it, right? Okay, and then you see the mechanical energy has 0.0050 and this is 0.0017. It has reduced. So why does this happen? Okay, so all these questions can be answered making use of this. Use your conservation of momentum knowledge, conservation of energy knowledge, and then ask them to work on this. Why does it happen here in this way? Why doesn't it happen in the older section? You can ask all these questions. Now comes your two-dimensional question. This year IB has introduced this. So I thought, okay, this is very important for us. Okay, so let me reset this. I can move the object here. Let me take this object here and I will change the velocity direction also. Change this direction like this. And I will change this velocity. See, this axis is very important. If I keep it here, then what do you think will happen? So will they collide? In the first juncture, they may not collide, right? Let me run this. After reflecting from there, there's a collision possible. So it's a very good animation to begin with, but they're not going to measure anything. That's what is the basic thing over here. Because any experiment, we should be able to measure something. Just viewing something will not give us that effect of doing science, right? One thing, so you can actually add the number of balls over here. You can add a number of balls. Good to see what happens to mass, what happens to the velocity, what happens to the momentum of the ball when you have multiple body collisions, so on. But we should be able to measure something. We are not measuring something here. So this is more smoother as compared to that. So gives a very good visual appeal. You click on this. This is what we can see. Both the balls move away. Right? So there's only one simulation you can see. You cannot see multiple hitting over there. See whether you can be able to see. Okay, you are able to see some values over here. The mass of the object, each are 1 kg, 10 and 40 meter per second, angle is 50 and 20. What we can do is, we can hit this initially. After hitting, the exit speed for the first object is 15.46, exit angle is so much. You can get something value here, right? And of course, you can change the value of coefficient of restitution also. Okay, this is a good one. Okay, so you can use this simulator to collect the data, ask the students to collect the data, and then analyze it using a graphical analysis, put them across like a line chart, understand why, okay, when the angles are changing. You can actually change the angles, right? Let me change the angles. I'm able to change the angles. I can, okay, position point is same, you can change the angles also. But will I be able to document that? That's the question. Entry angle 76.6, entry angle 20 degrees. What change am I getting? Let me just reduce this and simultaneously start doing it and see what happens. If I keep it here and I keep it here, both are on the same line, maximize this 90 and 90. Wow. Okay, then I am able to do it. Okay, maybe I can increase this also. I'll make this as, let us say 10, and let us say this is also 10. What do we see here? 10 and 10 with respect to the horizontal, 10 and 10 over here. And when I start the simulation here, they hit it, go away, and you see the exit speeds are different. This is what you get here. Total loss of contingent is equal to so much. Depends upon the coefficient of resolution. I can do wonders using this, right? Maybe I can use the same example as, for example, I can take of a golf or maybe billiards, for example. On a billiards board, I can take two coins, this one, and then using a cue stick, I can push it across. And I can find out, I can change the angles. Okay, I will initially be able to get, do I get a velocity? I may not get the velocity. That's a problem. Okay, I should be able to get a velocity. Maybe I can take two mobile phones, put it across, find out what is the velocity using your Firefox app, and then compare that, this one here. Then I can find out maybe this particular quantity, right? I can do wonders using this. So this is how one can actually use physics to understand things and see to it like how you'll be able to estimate the parameters, how to work on it, and all these things. Okay, so friends, thank you for being with me, and do like, share, and subscribe to my channel, share it with everyone. We'll see to it that novel experiments are being conducted, and see to it that the students also enjoy physics. Okay, not just learning from the point of view of examinations, but also, okay, try making physics more easier, not easier, I can say, try make physics making more fun, useful to all. Thank you. Thank you.